22nd, which is today, 24th, which is Wednesday, and then next week we have 2 days, and then we have exam 4. And then we have the 6th for review, and then the final is on the 8th. With these two, we're going to finish off enolates, and then we're going to talk about carbohydrates. Glucose carbohydrates are pretty uninteresting. We may start amino acids. We may not, depending how far we get. Wherever we finish on the 24th, that's material that would be fair game for exam 4. So the stuff that we do on the 29th and 1st, whatever we do there would just be on your final. All right, so everything that's going to be on exam 4 will be, the 24th is the kind of cutoff for content. So however far we get into carbohydrates and or amino acids, that's what's going to be on there. So it'll heavily stress enolates as well as whatever material we get with the biochemistry. And then we'll have the last couple of days to finish off amino acids, and I don't know what else do organometallics maybe? No, I don't think so. And then we'll just have the rest for review pretty much. All right, so your exam 4 is in lab. It'll be during the lab time. I think his plan is he's going to have you finish your presentations, try and do as much of them on Tuesday as possible. And then however many you guys still have left on Thursday, you'll do those first. And then after that, you'll start the exam. And so we'll just kind of have to play that by ear. This way you'll get a little bit more time, since I know that's something that's potentially preventing people like Eric from reading the directions. But that'll help you out. Okay, and then we'll review again on the 6th, and then final exam on the 8th. I'm going to put up a practice couple of questions for the final in that same format as the ACS exam, so that you can get used to the types of things you'll see as well as the speed of it. It'll be probably 105 material, so it's not necessarily going to be 106 because I'm going to be doing the same kind of practice thing for my 105 class, and so I'm not going to do it twice, if that makes sense, since your final does have 105 material on it still. It'll still be useful. So, all right, cool. Any questions on what else is forthcoming?
I just had a question
Yeah.
for the final, like
Yeah.
what the format is. Like, is it written or is it multiple choice?
So it's an ACS exam, so it's going to be 70 multiple choice questions, and you'll have a time limit of 110 minutes. And so it's 4 option multiple choice, so A through D, and it'll cover things from 105 and 106. I will try and put more emphasis on the 106 stuff, depending. So how it works is they send me a question bank, and normally it's not a question bank. They just send the exam, but since it's through COVID online stuff, it's a question bank that they send me, and so I have a little bit more freedom to choose. But since it's supposed to have 105 material, there's gonna have to be some on there. So it's a pretty quick thing. You have about a minute and a half per question. Some questions are going to be super easy. It's like, which one of these molecules has a carbonyl in it? It's like, okay, I can do that. But some of them, it'll be a little bit more complex. So it'll be through that. So it'll be on Canvas as like a quiz, where you'll take it there. And it'll be auto-graded and stuff. I forget the exact time of that, but that's something posted on the JCC website. Their like exact time frame of when the finals start. So that I'll look up I think it's on the syllabus too. I put the time that we're supposed to start that. It might be like 9 o'clock. They always do weird crap for finals, right? They have these weird times, so we'll look at that closer. Okay. All right. Any other excuse me, questions on this stuff before we finish up enolates? Cool. Alrighty. In that case, let's go ahead and continue off with Michael additions. So we just want to take a minute to remember that when you have an alpha beta unsaturated, actually, you know what? I want to let's talk about that synthesis problem. Hold on, let me finish this off first, though. Okay, so let's go ahead and take a look at the what we were supposed to do for the synthesis. Most of you actually did better on your first synthesis node on the exam, even if you forgot to show the synthesis for your intermediates, or other reactants rather. With that one, here it is. With this absurd molecule, which I understand was difficult, this was an intentional choice to make it difficult. This was the main thing that people kind of didn't quite get. Was that if you're ever synthesizing a secondary amine, that has to come from reductive amination. So you have to make it through taking an amine and an aldehyde or ketone and using the cyanoborohydride to reduce that imine down. So not a lot of you had this. Had something even resembling reductive amination. So I just want to make sure that that this idea isn't gone away, because since your exam is still cumulative, exam 4, right, it's going to focus on enolates and then that sort of thing. But, you know, in synthesis or mechanisms, it's still important that we remember back to these sorts of things. So I want to spend a few minutes today on that. So that was the big thing. Once you understand that since it's a secondary amine on primary carbons, that means it has to come from an amine and an aldehyde. And since this is symmetrical, it would be a symmetrical amine or symmetrical aldehyde. And so you have kind of two options here. You can either have this thing. Oops, forgot a carbon there. You can either have the cyclic bit as your amine or as your aldehyde. But if we consider that that cycle part, that the cyclic part has alkenes in it, remember the hint was that there's an aldol of some sort here. If you make it so that your butyl group is on the aldehyde, and then use it that way, you'll see what aldol are you going to do there. All right, so this is not going to be the part that has the amine. The amine is going to be our linear part, and then the cyclic part must be the aldehydes. All right, and then so once you've got this aldehyde structure, which would be whatever the opposite of the reductive amination would be, you'd break it into the aldehyde and the amine. At that point, I would hope you can see that that's where the aldol took place. So remember, an aldol is always alpha and or beta to your carbonyl group. So we have a ketone in this case. This is an aldol condensation because we have double bonds there now. An aldol condensation, remember, is you have a hydroxy group that gets eliminated with the presence of heat. And so if we then move backwards, I'm not going to worry about the amine part. Everybody seemed to know how to make the amine part, so I'm focusing on the aldehyde and the aldol part here. So this aldol must have come from condensing across those double bonds. That's where the hydroxys used to be. They used to be beta hydroxys before they were condensed down to the double bonds. And then from there we remember, well, now that we see where those hydroxys are, we can make the determination of having the alpha proton to the carbonyl, or rather the alpha carbon, is connected to what used to be another carbonyl. And since we have aldehydes on both sides and hydroxys on both sides, we must have used a dialdehyde. And so if you continue breaking this down, you'll see that you'll end up with a dialdehyde. 4 carbons, dialdehyde. And then, of course, just making the aldehyde, you can do it by making the alkene, brominating diene, make 2 hydroxys, oxidize them, and now you can do your aldol. So now in looking at the key, does it make a little bit more sense now? Do we see how this aldol took place?
Yeah.
I was just confused.
Yeah, I understand. Yes, you're in a time crunch and you're like, oh my god, this thing is just absurd. Oh, by the way, yes, Ani, it's all multiple choice. Sorry, I was looking at the chat. So, yeah. I'm glad Eric will allow it. So, that's the key bit to look out for. With aldols or clasins, you're looking for something that's happened kind of 1-3. You're looking at something and then something here. So you're looking at a 1-3 type addition. So, or something that's happened between carbons 1 and 3. So you have your carbonyl carbon, and then you have something else on the beta carbon, which is the, technically 1, 2, 3. So you're looking at something in a 1-3 relationship. With Michael additions, we're looking at 1-4. We're gonna look at those. We're gonna start that up again in just a second. So in terms of what to look out for, aldols and clasins always give you 1-3 products. So either that's the aldehyde and hydroxy, or ketone and hydroxy, or it's an aldehyde or ketone and a double bond. And that'll be an alpha-beta type situation. So still 1-3. The functional groups there that end up. Okay, so cool. All right. So just remember also, I do have office hours today, as I do on every Monday, from 12:15. That is usually when Eric comes to bug me, so you are free to also come to bug me during that time. Narek also bugs me during that time too. So, cool. All right. So back to Michael additions then. So remember that these are additions to an unsaturated aldehyde or ketone, specifically to the position that's going to end up giving us a 1-4 addition. We're going to add something here and add something to the oxygen. We're going to add a hydrogen to the oxygen, right? So we're going to add our nucleophile to position 1, and we're going to add a hydrogen to position 4. And remember, they're going to tautomerize later, but that's the idea here. This happens, of course, because if we consider resonance, here, you end up with a positive charge on that carbon. And so that's why that position is so susceptible to nucleophilic attack. all right, is because that resonance ends up giving it a positive charge there. So you have a delta positive in that position, so it's ready to go ahead and be attacked. However, we remember also that only that strong nucleophiles which are unstabilized enolates or Grignard, these things attack the carbonyl. They don't wait for this resonance and all that to happen. They just go straight for the carbonyl. They don't attack that beta position. And so if you were to take this aldehyde and put it with a Grignard, let's see, we're going to want an acid wash. We're going to just attack the aldehyde, and we're going to end up with a hydroxy group there. So strong nucleophiles go directly for the carbonyl. They don't go for that beta position there. Remember the beta position. Alpha to your carbonyl is here, so beta is that one. Beta is the other side of the double bond, farther away from the carbonyl. However, we saw that with a milder nucleophile, like something like a Gilman, yeah, we'll just need the water wash here. We will, in fact, add that to our beta carbon. So, so notice we've added an ethyl group, which I'll do in blue here. The new bond that's formed is the purple one. So we have now added 2 carbons to our molecule along where that double bond used to be. And remember, the idea for this sort of thing is we have our stabilized ethyl group, ethide, comes in, attacks, pops this thing open, resulting in an enolate. So we're going to end up having an enolate here. And if we add water and then tautomerize, we end up getting our product there. So that's the sort of mechanism here. Interestingly, however, what we can do with this is we don't have to put the water in right away. We can actually say, well, we've got this enolate there, and it's just waiting. It's just waiting for water to come along so it can protonate itself, and then it can tautomerize to the aldehyde. What we can actually do is we can say, well, let's just put this with another electrophile. We can say, let's put this with an alkyl halide. And if we do that, then we can have this alkylate again. We can say, aha. Close that down and have the enolate attack something. So, in being attacked by the Gilman reagent, our alpha-beta unsaturated compound becomes an enolate. We have the option to add water and get back our aldehyde. However, if we wanted to add some electrophile in there, we can have our enolate attack it. And in doing so, we're going to end up having our methyl group here. And in fact, I'm going to do these a little bit unusually. I'm going to show you where these groups are in our new molecule. And of course, we'll just kick out the iodine. Who cares about the iodine? Leaving group, it's gone. In this case, we've now added two things. We've added to the alpha position a methyl group, and to the beta position an ethyl group. And that was because we did a Gilman first, and then a alkyl halide second. That gives us the beta position, and this will give us the alpha position. So if we want, we can go ahead and react this again. And so as a result, we got the ethyl and then the methyl on this. So we're adding first to the beta position with a kind of moderate nucleophile, the Gilman reagent, and then we're using an alkyl halide to add something to the alpha position. And it could be anything that's an electrophile, right? We could add, let's see, what we'd like to add. Anything that's electrophilic. So we can add, we can do, like, we could add a tosylate, have that be removed, alkyl halides. We can add, if we really wanted to go nuts, we could do some sort of crazy carbonyl compound. Probably a little bit less easy to do. But that's another option, right? So typically, though, this is alkyl halides, tosylates, that sort of things. Things with nice leaving groups. So those are pretty common there. So we're going to add first to the beta position. We get it in the intermediate. We have the enolate. Enolate can be quenched with water to give us just the regular added one thing to our molecule, or we can add a second thing if we so choose by using something with a leaving group.
So this wouldn't work with Grignard necessarily?
No, because Grignard is just going to go ahead and attack your carbonyl directly, and so you end up with this. And at that point, that's not going to attack an alkyl halide or anything. So as soon as you put in your Grignard, you've made it no longer a carbonyl compound. All right, and it just happens because the Michael addition intermediate is an enolate. The intermediate for a Grignard is an alkoxide. And so, I mean, technically, if you wanted to do a Grignard and then a Williamson ether synthesis or something crazy like that, like, you can do that, but that's not very common, I would say. So with the Grignard, you're only attacking the carbonyl, and then you're pretty much done. With this, we have the option to add more stuff. All right, if we look at this a little bit more, remember that the beta addition nucleophiles we saw were stabilized enolates, or we have what did I just say? Oh, the Gilmans, yeah, duh. Remember, stabilized enolates have two electron withdrawing groups on them. So something like this, where we have, I'm going to just draw it as the carbon ion there. So stabilized enolates have two electron withdrawing groups. These can be esters, ketones, aldehydes, nitriles, nitro groups. all of those would be stabilized enolates. So it's got to have 2 of them. So that could be cyanide. The geometry is terrible. Let me try that again. There we go. Something like this, or you can have something like that. Something that's stabilized. A stabilized enolate can add to the beta position. And then, again, you can then add something else to the alpha position if you want. If you want to add an electrophile there. And of course, the Gilman is your dialkyl lithium cuprates. So whatever of that you want. These stabilized enolates, again, have to have 2 electron withdrawing groups. If you have only 1, you attack the carbonyl. So you don't get a beta addition. You're not adding to the beta carbon there, you're adding the carbonyl directly. So something that's just a single enolate like this is going to attack your carbonyl of something, and you're going to get a regular aldol happening here. So you're not going to get this Michael addition. All right, so the idea here is you can use a stabilized enolate that will attack the beta position of your alpha-beta unsaturated system. Remember that these are Gilman donor, or not Gilman donors, Michael donors. Oh, that's terrible. These are all called Michael donors. So all of these stabilized ones, and again, any combination of these. We can have an ester here. Whatever, it doesn't matter. An ester on one side, a nitro on the other, an ester on one side, a ketone on the other, a ketone on one side, an aldehyde on the other. Doesn't matter. Mix and match your electron withdrawing groups, but you need 2 of them. All right, all of those will be Michael donors. They will attack the beta position. If you only have 1, it attacks the carbonyl, just like a Grignard. All right, so hopefully that's super clear since I've said it 10 times. But we'll take a look at some of these in some reactions. And then if we just recall our Michael acceptors are an alpha beta unsaturated ketone, aldehyde, nitrile, or nitro. Not an ester though, no. So what are those for? So we looked at aldehydes, right? We could do it with a nitrile instead. We could say, I forgot the geometry. By the way, don't mess up your geometry. I noticed that some of you were putting weirdly bent nitriles. Remember that this is an sp carbon, so it has 180 degree bond angles, so don't forget that if you're drawing a nitrile. But this would be an example of a Michael acceptor, right? It's got a conjugated double bond with your electron withdrawing group. Something like this would also work. A nitro group is also going to fit here. The idea here is that when something attacks the beta position, you have somewhere to resonate. So, because as soon as your nucleophile comes in here, it's going to come in, you've got to have somewhere to resonate if you're going to be a Michael acceptor. Same thing with the nitrile. We have places to put these extra electrons. That's necessary for a Michael acceptor. All right, so let's take a look. Let's put some stuff together. Okay, here we go. And so we'll do step 1 as this dude. Step 2, we have to have a base as well, right? What base shall we use here? Let's use sodium methoxide as well as our Michael Acceptor. And for this, let's also put in to everyone's favorite 2-bromopropane. And let's take a look at what this will end up producing. So notice since I'm using an ester here, I'm using the conjugate base of the ester as my base. I could use sodium hydride or LDA as well. Those would work. Although, since this is a it's a beta aldo ester, it probably is just fine to use the methoxide. That's a strong enough base to get this done. You can't use hydroxide here, though, right? Hydroxide, what will happen with hydroxide if we use that as a base?
It'll attack the alpha position?
Not quite. If we put this with NaOH, attacking the alpha position would make our base, right? That's what we would like it to do. But what will happen as well, so that will happen, yes, you're absolutely right, Eric, it will deprotonate that alpha position. But we also run the risk of this thing happening. We run the risk of hydrolyzing our ester. Because remember that esters are base sensitive. Right, so if we put OH minus in there, we have the potential to attack the carbonyl, open it up, kick out OMe. And then we're left with a carboxylic acid, which is just going to do other things. So we want to use, if we use this base, just like with our Claisen reaction, if we're using the same base that is the conjugate of our ester, we avoid that problem. Right, because if it attacks the carbonyl and kicks out methoxide, nothing has changed. So we don't end up with anything different. Okay, so that's why we want to do that. We could also use KH or LDA, but those are not necessary for this sort of thing. If we had a dialdehyde, Eric, though, go ahead and use NaOH, no problem. It's when we have an ester there we have to pay attention to our base if we're not using KH or LDA. Cool. Okay, so let's see what's going to happen here. So first step, of course, we are going to end up making our stabilized enolate. And let's have it go up this way. Why not? All right, so we have our stabilized enolate. Since it's stabilized, it's going to be able to act as a Michael donor. Michael donors attack the beta position of a Michael acceptor. So, if we include our Michael acceptor here, we're going to attack it and bump everything up to our nitrile. And so we're forming a bond between our alpha carbon of our Michael donor and the beta carbon of the Michael acceptor. So those two, the purple dots, are going to be where the new bond is formed. So I'm going to just keep the top part the same. We're forming the bond here. So we have our purple carbons here. This is our new bond. And if we just put everything that's going to be on that, well, we've got our new bond there, that carbon. We have a double bond. And then we have an additional double bond to our nitrogen. And so, this is analogous to an enolate. We have a nitrogen instead of an oxygen. But this is the analogous step to our enolate. And so we see, okay, well now we've got that bromine thing there. If we were to just acid or water wash this, we would end up with just the nitrile, and we would end up protonating that position, right? So if we want to add our propyl 2-bromopropane to this molecule, we can do that. We're going to close down, reform our nitrile, and now this enolate is going to go ahead and attack our alkyl halide. Our new, we're going to have the red carbons this time. The red carbons are going to be bonded together. And everything else stays the same. Alright, so those are our purple. Here's our red one. That's the part that's going to have the isopropyl group on it. And then we have our nitrile still down there. Alright, so we have our purple bonds that we formed on the beta position of our nitrile. And then we had, on the alpha position, we've added our other thing. So we formed two new bonds here. And remember that this is the alpha position, this is the beta position of our Michael acceptor. So we've put two things on there. We've put our Michael donor on the beta position, and we've put our alkyl halide on the alpha position. So it doesn't matter what your Michael donor is, that's always going to go on beta. And whatever if you have an alkyl halide or something, electrophile on your, as your second step, you'll then attack it and put it on the alpha position. Alright. So do we see how this product was formed?
Yes.
Cool. Cool. So 1.4 edition for this. Let's do another one. Let's say we've got so I'm going to just put in an enolate already. And then ethyl iodide. Let's see if we can't predict the products here. So I'll give y'all a second to work on this. and go ahead and do that. Try and figure out the product, and then I'll do it. Or we can discuss it. You can just do the final product if you want to do the intermediate. Might be a good idea just for practice, but yeah. Okay, go ahead. Alrighty. Do we think we've got it?
Not yet.
Maybe. Alright. So you should get the following. Oh well. 1, 2, 3. And then on the alpha carbon, we should have an ethyl group. So this should be what you've ended up with. Although I think I might have too many carbons here. 1, 2, 3. Attack that one. I do have too many carbons. Whoops. Okay, hold up. So this used to be the double bond, and then we have the NO2 here, and then on the alpha carbon we have our, there we go, our ethyl group. So this should be what you've gotten then.
I'm not comprehending it. Can you just draw where the double bond used to be?
Poof.
Oh, right there. Okay.
Right there. Yes. So it was because I had the cyclohexene bit here in the wrong geometry. I was very sad because I wanted to just draw it as if it were on the, here, let's draw it that way. So, right. So on the alpha position, we're going to add our ethyl group. On the other position, we're going to add our cyclohexane bit. Although now that I think about it, I have an extra carbon in my Michael acceptor. That's the problem. But do you see that's where we would form these things? This would be alpha and beta. Had I given you the correct Michael acceptor. There's too many carbons there. But I want to focus on the bond making before we fix that. So do we see that there? That's the addition part we've added to the alpha carbon, the ethyl group. To the beta carbon, we've added this cyclohexyl thing. Alright, so this really should be this if I were better. Because with the nitro, remember that the it's got to be directly adjacent. So, because the resonance that's going to happen has to be right here. So if we have that extra carbon in between, it's not going to be able to resonate. So forgive me there. But the point is here is on your double bond, you should add your Michael donor to the far away side of the double bond, and then you'll add your alkyl halide to the closer side of your double bond. Okay?
So unlike the last problem we just did,
Yeah.
so last problem we had to make a double bond, but in this case, if we already have a double bond, we would just attach
What do you mean
the.
we had to make one? It was right here. In the last case, I gave you your Michael donor as your like starting material and the Michael acceptor as your reactant. In this problem, I gave you the opposite. So I had already given the this bit here. Remember that could be. Oops. That could be this. Right? Those two are resonance forms of each other.
I was gonna ask if you could do a mechanism like.
Yeah, we can do that. Okay. All right. So first step is we're gonna have this bit attack here. Yeah, let's have it attack. So is it okay if I just do it like this? Oh, I've got to draw out my nitro then. So let's give some fun carbons different colors. So purple and purple shall be connected. So do you want me to keep the nitro part the same way or the cyclohexadione the same way? Like, because I'm going to have to change the geometry a little bit just to make the zigzags work. I'm going to keep the nitro where it is, if that's okay. And I've also drawn it again with too many bonds. Okay. So we now have our cyclohexadione thing. I'm going to actually put it this way just so I have more space. Is that 6 members? No. Ugh. There we go. God, that's ugly. Okay, let me try this one more time. Lovely. So our purple bonds between the alpha carbon in between those two carbonyls and the beta carbon of our Michael acceptor. And now second step is I didn't draw my ethyl iodide. Close down, and then this attacks our alkyl halide. And if we're going to do these with red, purple bonds are still there. And now we have on this carbon, we have that ethyl group. All right, so first step, Enolate attacks. Michael donor attacks, I should say. That attacks our Michael acceptor, pops that open, forming the analogous to an enolate type thing. That closes down again, reforms that N double O, double bond O, and then I don't want to say enolate, but the enolate analog, if that were a carbon, it would be an enolate. It would then attack your alkyl halide, putting therefore your ethyl group on the alpha carbon. So does that make it a little bit more clear?
Yeah,
Okay,
it did.
good. So,
So you said the difference between this one and the last problem was that we used the Michael Donor.
so it just, I mean,
Sure.
like last time I gave you the minus part. Is it like if I were to give it in the same thing, I would do like. Like this is the only difference. I gave you the other one as your starting material. Doesn't really matter, right? You just got to put them together.
Okay, that makes. Okay, thank you.
Yeah. No problem. Alrighty, and just remember that this thing is equivalent, or they're resonating between the one with the double bond and the one without the double bond. So you can see it in either way, right? You can see it as the enolate form or as this carbanion form. And it doesn't really matter which one. I mean, in theory, the enolate one is better because that's just more likely to be there. It's the bigger resonance contributor, but it's fine either way. Okay, cool. We have 2 more reactions to cover in this, and then we're pretty much done with like actual reactions. The rest of the carbohydrate stuff and the amino acids are boring. They don't really do much chemistry, as it were. So we'll take a look at those. This next one that we're going to talk about, the stork enamine synthesis, is a way to turn something that normally can't be a Michael donor into a Michael donor. If we were to say take this and give it it is unlikely that we're going to get a Michael product, right? We're going to end up just attacking our carbonyl directly, or we'll attack another one of these cyclohexanones. We're not going to get the Michael product here. But we're going to see that if we... there is a way to make this kind of single carbonyl molecule do a Michael addition. And that's by making it into an enamine first. If we take... I guess I need to rearrange that. NHR2. Remember, we can make an enamine by condensing an amine, a secondary amine, onto our carbonyl, onto our ketone. And we see here now that an enamine CF compare with we see some similarities here, yes? We see that, it's very similar to an enolate, although because an enamine is neutral, whereas an enolate has a negative charge, the enolate's going to be more reactive, right? It's got a negative charge, it's less stable. And we saw that the more reactive nucleophiles don't do Michael additions. They tend to just go straight for the carbonyl, and then they'll do aldol. But it turns out we can take this, create the enamine, and then use that. That will also be a Michael donor. We're going to be able to attack something with this enamine, which is kind of like a a less reactive enolate. So we can say, well, I'm going to take this enamine now. Doesn't matter what your R groups are, the way we're going to get rid of this later, so it doesn't really have a huge effect on us. If we take our favorite aldehyde, unsaturated aldehyde here, we can, just like before, have a bond formed between our alpha carbon of our donor and the beta carbon of the acceptor. And in doing so, and as always, I'm going to have to, okay. I'm going to just draw this bizarrely. Okay, whatever. Boom, 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 boom. So, I guess technically we've got our enolate, and then if we use water or an alkyl halide, we can get the second part on there. Let's just use water. And I'm just going to protonate this if that's okay with everybody. Actually, no, let's leave it as the enolate because you'll see later. So, we will have now attacked purple carbon forming bit here. Alpha to the, now it's an iminium, the enamine alpha carbon, and the beta carbon of our unsaturated aldehyde. We form the enolate. And interestingly, once we do our water wash, or if we use acid, generally it's more common to use acid here, we end up with a diketone. Or I guess this will be an aldehyde, a dicarbonyl species. So again, we have our new bond formed there. Remember that H3O plus, when you treat an imine or iminium with NH3 plus, with H3O plus, remember that just hydrolyzes it to the ketone. Right? You can make an imine or enamine by using an amine and a ketone, and if you use hydrolysis, would be the opposite of that, splits them back up again. So we end up losing our amine, although it's probably going to be protonated, whatever. And we end up now getting the ketone back that we started with, as well as our new Michael adduct. So we have added to that beta position. All right, so it's a way of having your Michael donor kind of hide. So, you know, a ketone normally is too strong of a nucleophile because it's not stabilized. It's too strong of a nucleophile to do it, because instead of the Michael product, you're going to end up with an aldol. You're going to end up with the aldol product here instead. Maybe condense it, maybe not, but whatever. You'll end up with this product. And that's not what we're interested in here, because that one's attacking the carbonyl. If we wanted to attack the double bond and get the Michael addition, the beta addition to happen, we need to kind of hide it by treating it as an enamine instead. So the reagents that were necessary here is, first step, make the enamine by using a secondary amine and acid. And then we can add in our Michael acceptor. And then third step, acid wash. That will end up getting us to treat a single ketone or a single nitrile or a single nitro group as I mean, I guess we can't really do this with these with nitriles because those aren't going to condense. Never mind. Ketones or aldehydes. That's going to be more specific here. Your ketone or aldehyde as an enolate is too strong to be a Michael donor by itself. However, if we condense it down to the enamine, then it becomes a weak enough nucleophile that we can have it attack in a Michael addition type way to the beta carbon. And then we acid wash, which hydrolyzes our imine back to the ketone, and then we have our other bit there. So in that case, that's we have a aldehyde. All right, so this is just a modification on this. So if we have a not suitable candidate for Michael addition, we can still do Michael addition if we make it into an enamine first. So let's see if we can't figure this out. Let's do a problem. Oh, that's ugly. Okay. Let's see if we can figure out what reagents would be necessary here to go from our starting acetophenone to this diketone species. By the way, the hint that you're going to end up with, that you need to do a stork enamine synthesis on this, is that you end up with a 1,5 dicarbonyl species. Stork always gives you a 1,5 di C double bond O. Whether that's two ketones, aldehyde and ketone, two aldehydes, doesn't matter. Two carbonyl compounds in a 1,5 relationship. So, like, aldol and claisen give you 1,3. Stork gives you 1,5. Michael, regular Michael, gives you 1,4. So, it's all about identifying the relationships in the products. So, 1,3 claisen or aldol, or the malonic ester, all those are all variants of the claisen, right? Those will all give you 1,3. Michael addition gives you 1,4. Stork gives you 1,5. So, anyways, what are we thinking here to use as our reagents?
Diopters are secondary. I mean,
yeah. Which secondary amine would you like to use?
Does it matter or not?
Does it matter or not?
I don't know, 2 methyl groups.
I don't know, 2
All
methyl
right.
groups.
You'll say two. Never mind.
2 methyl groups is fine. Okay, great.
Okay.
What's next?
Probably think that we want.
Yeah, and what's that?
So I haven't gone far enough.
Okay, that's okay. That's okay. That said, I have given you a little hint with these purple bits.
Probably like a ketone.
It will indeed be a ketone, but what's the ketone? In the meantime, I'm just writing this here just so we see. So the new bond that's formed is between 2 and 3, which tells us that our double bond must be between 3 and 4. So if we pretend this isn't here, that's where our double bond used to be. Remember, it's always one carbon. It's a conjugated thing. So double bond, single bond, carbonyl. And so therefore, everything else must be from this. Because once this thing is negative, that's when it attacks the double bond here, and that's where you form your new your bond between carbons 2 and 3 in your product. That's the new bond that's being formed there. Oh, I guess we'll also need a well, we're not going to need a base because we're making the enamine. And then last step, of course, water, acid wash. But the hard part here is figuring out where your bond is going to be, and it's actually quite predictable for a stork reaction here. Your new bond is always going to be between carbons 2 and 3, and your double bond will be between carbons 3 and 4. So if you just pretend the bond 2 and 3 is not there, draw your double bond between 3 and 4. So your double bond used to be 3 and 4, if we consider this.
So in the last
Yeah.
problem, it was 2 and 3 as well.
Yes. So notice 2 and 3 was our new bond, and 3 and 4 is where our double bond used to be, and we see that in reactant 2, right? We see the double bond there.
Oh, you started your count earlier. Okay.
Yeah, you go from carbonyl to carbonyl. So ketone to aldehyde, ketone to ketone. So number 1 will be your original Michael donor, carbonyl. So wherever that happens to be, and then 3 and 4 will be on the other side. You could do this the other way. You could have your acetophenone part be the Michael acceptor. You could have this done either way. You could have it done where you're taking You could also have it do this way. You'd get the same product using the same reagents. The enamine and then the if you switch them. And you'd still see that at the end of the day, you'd still have your double bond be in one of these products, and then you'd have your new bond between 2 and 3, although the number would be reversed. And this time number 1 would be this dude. You'd have your new bond formed between 2 and 3, and your old double bond used to be between 3 and 4. So if this is the second way we did it, those are those carbon numbers. So it's always your donor that starts as carbon 1, and then your acceptor would be 3, 4, 5. So donor has 1 and 2. Acceptor has 3 and 4, and then 5. 5, which is double bonded to O. 1 is double bonded to O. 3 and 4 are double bonded to each other. So the patterns for a stork are very consistent. All right, although it's probably less good to do this second route than it is to do the first route. The reason being is with this donor here, you have the potential for the enamine to be formed on either side, right? You have two different alpha positions here, whereas in the acetophenone up top, we only have one place for our enamine to go, and that would be here. Right? We can't make the double bond the other way because that carbon doesn't have any hydrogens on it. So it has to be on that side. With the other one, we run the risk of maybe making the enamine on either side. So it's less, you could have it there, or you could have it here instead. So either way. In either case, it's not the better choice because you have that option, and therefore you could get a mixture of products. All right. All right, so I just want to talk about the last one here first, really quickly. Okay, the Robinson annulation. Annulation means ring making. And really this is just going to be a Michael addition followed by intramolecular aldol. So first Michael addition, second aldol. And we'll take a look at something like this. So classic example of your Robinson. And we're going to make this super easy for us because we're going to have it all organized for you. You're going to end up making an additional ring here. Oops. No, that one will stick out. This is the product that you'll end up making. So you'll end up with a new ring being formed. And then you'll also condense back down. And we'll take a look at this. It's two things. So first step is the Michael addition. The Michael product I'll go for first, and then we'll look at the mechanism here. So the Michael will end up having us attack purple bonds or purple carbons. Right, we're going to do a 1,4 addition. So this other methyl group just goes away. We have our new bond here. This is the other purple carbon. Everything else stays the same. This is the product of the Michael addition. And then we will do an aldol condensation. I can fix this. Yes, Michael. Oh, that kind of looks terrible. And then this is the aldol. So Michael addition first forms this new bond between the purple carbons, alpha carbon of the enolate, and the beta carbon of your Michael acceptor. And then later we're going to see, well, we're going to form a new bond between the blue carbons. And technically that's going to be, first it'll be this OH. And then instead, as before with an aldol condensation, we're going to get rid of that OH and have it now be the double bond. So our purple bonds that are being formed are here, and the blue ones are going to be down there. So we form 2 bonds in a ring together. Alright, so let's take a look at the mechanism, and then we'll just pick up with this on Wednesday. So, of course, with this we have, we're going to need a base to make this the enolate, so we'll do that first. Let's use NaOH, why not? Comes in, pops this open. Again, could be either side. We're going to form an enolate here. It's a stabilized enolate because this is, it's got the diketone. So there's our enolate. It's going to find our Michael acceptor. Four arrows there. Purple bond being formed between carbon and carbon. So that methyl group is still there. We have our ketone back, both of them. And now that purple carbon has formed a new bond to the other purple carbon. Which now has, now has the double bond there. And its methyl group. And now take a look at what's going to happen. This is the aldol part now. This closes down and attacks our carbonyl. Since we already have the enolate. And I'll do the colors in just a second. Let me just draw all this stuff. Oh, I'm sorry. We need to do an equilibration first. I'm sorry. So, with this step, I forgot we have to move our aldol over. What am I doing here? There. Allergies, you know how it is. We'll have our water here. We're going to have to do this kind of in 2 steps. That's going to go ahead and form the carbonyl again. So now we've got this. Now our base that we just formed will come in and grab that proton, thereby opening up on the other side, and that's when we're going to have it attack the carbonyl of the other half of the molecule. Keep everything the same. There we go. Now we can have this attack a bit more reasonably. Pops that carbonyl open. We end up with the following. which then, if we protonate it, we can go ahead and do that. Regenerating our base, and apparently I'm using purple arrows now. And remember, because this alpha proton is acidic, that can be abstracted easily, leading to the elimination of a hydroxy group, which will then give us our product. And then we regenerate our base again. So we end up with this product. All right, so look at that again over the next couple days, and we'll continue on Wednesday. All right, so it's really just a Michael addition followed by an Aldol condensation. That's all that's happening here, but this is terribly confusing because it's putting two relatively difficult reactions together at once. So this is especially nasty. And as you can imagine, it is a favorite of organic instructors to throw at their students for exams. So, good stuff. Alrighty.
It's not your favorite.
All right. So that's it for today. So I'll see you guys at office hours.